Hello and welcome. We are into our module 5 of the semantic web technologies course. And in this module 5, we are going to talk about the web ontology language, or in short, OWL or OWL, right? So till now, what we have discussed about the resource description framework, which is a kind of framework by which you can represent knowledge about the entities on the semantic web. So basically, you are describing the entities with a set of descriptors which are called the metadata, and this metadata is represented using this RDF framework, and this RDF is basically is used to describe the properties of different entities, the real entities that are there on the web, semantic web, but in particular. Now, in order to organize the knowledge that we are putting into this RDF form, we have talked about the RDFS, which is basically the RDF schema, which is kind of terminological knowledge. It's a kind of overlay over the raw RDF data. So, and we know that this RDFS vocabulary, they help us to organize the RDF data in a very structured way, right? By using the vocabulary items like subclass or some or subproperty or something like that. Now, if we want to encode much more complex knowledge about the entities, and uh, so you want to go beyond this definition of the subproperty or subclass or defining a class itself, we want to achieve more. We want to make our language more expressive so that we can ideally express knowledge about anything in the on the semantic web. And that particular with that particular motivation, this web ontology language was coined through W3C consortium, and this has been standardized in different stages. So earlier we used to have web ontology language or OWL 1.0, then we have OWL 2 or OWL 2.0, right? Now, as we add more features, you know that the language is getting more and more expressive, right? So in this module, we will be talking about this web ontology language, the semantics of the vocabulary items we have in the web ontology language, and finally, we will see that what kind of logic framework we can attach to the semantics of this web ontology language, and with that particular logic framework, we will be coming up with the reasoning algorithms which will help us to reason about OWL data or web ontology language data, right? So this will be the kind of objective for this particular module 5, right? So to provide a summary of the things that we are going to talk about is so this web ontology language, it is a kind of language for defining an ontology. So we have already discussed in brief that an ontology really means a conceptualization of a domain, right? So it is a formal conceptualization of a domain. And if we have an ontology, this will facilitate many things like the shared understanding between the agents on the semantic web, right? And it is more expressive than RDFS, right? And this OWL, it has got many dialects. So if you are using the full functionality of OWL, that is called OWL full. There is another dialect which we call as OWL DL, which is a short form of OWL description logic. So this is a bit lighter version than full, but it is more or less a bit comprehensive and complex also. And finally, we have got OWL Lite, which is the most simple OWL language dialect, right? Now, there are different development platforms, and one out of them is Prodigy, which is very popular in the design of ontology, right? So, if you want to design an ontology for a domain, this particular tool will be becoming helpful, right? And the semantics of owl is captured through the description logic, which is a kind of logic family. In short, we call it as DL. And the description logic, it has got also different families, right? So we can have like something like ALC, shake, shoin, shriek. So there are many families of DL. We'll be talking about them later. So you see, we have used different alphabets. So these alphabets, they have particular meaning. And this alphabet will tell you what are the kind of constructs of description logic is included in a particular logic family, right? And for every such family, there are reasoning algorithms. So these reasoning algorithms, they are called Tableau algorithms. We'll be seeing how we can use Tableau algorithm and a different set of rules attached to different families to perform reasoning over the description logic data, right? So this is the kind of thing we are going to discuss in this module 5, right? Now, as we are talking about the language for describing an ontology, let us think about what we mean by an ontology. So, we have used this term in this course from the very beginning without defining it formally or properly, right? So there are many definitions of ontology, but I think this is the most widely used definition, which is by Gruber back in 1993, right? So the definition as per Gruber is ontology is a formal specification of a shared conceptualization of a domain of interest, right? So let us try to disintegrate this entire definition and try to analyze what we are trying to really mean, right? So we start with the domain of interest. So we have a domain of interest. For example, you can be having, say, an academics to be a domain of interest, or you can be having, say, space missions to be a domain of interest, or you can be having, say, economics to be a domain of interest, right? So you fix your domain of interest, right? Now, what do you mean by conceptualization? So when we talk about conceptualization, basically we think about what are the important concepts that are relevant in that particular domain and what are the kind of relationships these concepts do have among each other, right? So basically, mentally you are having this kind of structure. So you have got concepts and their relationship, right? So they basically constitute the conceptualization of a domain, right? But again, this is a kind of embedded thing in your mind or human mind. We need to put it in a formal term so that they can be represented computationally and they can be processed computationally. So for that, we need to have a formal specific, right? So what will this formal specification consist of? So it will be consisting of the mathematical definitions of these concepts. So we need to think about how do we represent them mathematically. And as we have talked about earlier, we will be taking help of logic to do that, right? Logic as well as set theory, right? To do that. And if we do that, so they will become the knowledge that we are encoding in this form. This knowledge will be machine processable. So I need to write machine processor, right? And we can write algorithms that can perform reasoning over this formally specified representation, right? Now, why we are asking to have this conceptualization? So that this we can develop a shared understanding, right? And this understanding will be shared among, say, group of, say, applications. It can be among group of services, web agents, or maybe the people, right? So you can see that we can represent this definition visually in this form, right? So the core of this idea is to how do we really formally represent uh, a piece of knowledge about a particular domain, right? And that thing is called basically ontology, right? And so basically this part will be the kind of point of discussion for this module. Now coming to the question, what's there in an ontology? right? So let us have a closer look what we have inside an ontology. So as we have specified earlier that ontology consists of mainly a set of concepts, right? And these concepts, they are also called classes, and these are represented mathematically as sets of individual, individuals, right? And apart from that, you can define a hierarchy between different classes, right? So that is also important. It is not only that you are having only classes, and along with the classes, you can have hierarchy among the concepts or the classes, right? So let us have a look at this one example hierarchy. So you have a person which is a top class, man and woman, they are subclass of person, father and grandfather, they are subclass of man, aunt and daughter, they are the subclass of woman, right? Now then we have properties. So you can think of this subclass relationship to be also a property, but this is a kind of special property. So that's why we are keeping this aside. But apart from this subclass property, you can have other properties, right? And they are kind of acting as roles of slot. So for example, one woman can be married to a man, or a man can be married to a woman, right? So if you see that married to be a slot, that is filled up by a particular woman, right? So that's why they are also called slots, and also they are called rows, right? Uh, Now the kind of examples we can have for properties like say a person can have a parent, person has got an ancestor, woman is a wife of a man, and man has wife, say woman, right? Uh, and apart from these concepts and properties, you can have in your ontology some axioms or predefined relation, right? So these axioms, they are always treated to be true. They are kind of your uh, background knowledge, which you always treat to be true, right? So if we try to take some example, so what axiom can we can put in this particular domain of example? So you can say that has ancestor is a transitive property. If x has got ancestor to be y and y has got ancestor to be z, then we can infer that x has ancestor z, right? So this we assume to be true. Now also you can define something like a person can have at most one father or mother. So what you are doing, you are trying to restrict the number of elements and a relation for a particular subject can have. And this particular restriction is called cardinality restriction, right? You can define also what do you mean by a grandfather class. So these are all called axioms. So you can define as many axioms as you can, right? Now out of doing all these things, so these are kind of representation you are doing. So what is the fruit you are getting? The fruit is really you can perform some reasoning tasks over this represented data, right? So let us see what kind of reasoning tasks we can do. So basically these are the things that are there inside an ontology, right? Now if you have this thing you can do, this is the thing you can do, right? So we can say that whether a given individual belong to a particular class or not. So for example, if I describe some properties of an individual and say whether that individual belong to a grandfather class or not, right? So that process, that reasoning task is called classification task, right? The second reasoning task you can perform to say whether a class is subsumed by another class. So for example, can I infer that a father class is a subclass of a man class if it has not been explicitly specified? So that is what we call as subsumption, right? And thirdly, if we can perform consistency checking, whether the definitions are or the axioms they are consistent or not, right? So for example, you have defined say a person can have at most say one father. Now you have an individual for whom you have got two relations has father and both of them are having value. Then you know that you have some consistency related problem. So these are the things you can do over reasoning, by reasoning over the ontology, right? Now, whenever we are designing a language for describing or representing one ontology, you have to put forward a set of requirements. So, the first requirement is that it has to have one well-defined syntax. So, as it is a language, if you do not have a well-defined syntax, then whatever you will be writing, that may be interpreted in different ways. So, that is what we don't want. So, it needs to have a well-defined syntax. Also, for every element in the language, you have to provide with a well-defined semantics. What do you mean by a particular construct in the language, right? So, for example, we have seen in RDFS something like subclass, right? And we know that we can define this subclass of relation with the help of say set theory, right? This set theory gives us a very nice way to define the semantics of subclass of very concretely, right? Not only that, so we have this. So if we have these two, we have a language in, right? Now, say you have written something in this language. You have designed an ontology, right? You have designed an ontology out of this, but is it like your ontology will come up with some reasoning in an efficient way, right? So you need to support an efficient way of reasoning new information out of the existing information in the ontology, right? So that is another prime important requirement, right? And fourthly, your language should have sufficient expressive power, right? So if I give you a very complex knowledge requirement, it has to be represented in using this language, right? And finally, you have got convenience of expression. So is it easy to express something with this language? Now you can see that all these requirements, they cannot be satisfied fully at a single go. So for example, this efficient reasoning support and sufficient expressive power, they are kind of having opposite effects. So for example, mutual opposite effects. So if you say that your language is having more expressive power, so that will mean that your reasoning algorithm might not be that efficient, right? So you need to strike a trade-off, right? So you want to be expressive, more or less sufficiently expressive, but not at the cost of having one inefficient reasoning algorithm, right? So you need to think of this while you are designing an algorithm and a language for representing the ontology, right? And also these two, so this sufficient expressive power and convenience of expression, they are contradictory. So if your language is more expressive, it might be the case that your ease of expression is not really that great, right? So with all this, we need to think about what kind of language we can think of, right? Now, while we are talking about the language, we need to think about what would be the semantics of the individual constructs in the language and how they are leading to the reasoning, right? So, for example, can we define some construct to represent class membership, right? So, if X is an instance of C and C is a subclass of D, then we should infer that X is an instance of D. So, we have done this using RDFS, right? So, this is a kind of example of formal representation of something and that leads to reasoning, right? Can we define equivalence classes? So, for example, if we define A to be equivalent to B and B to be equivalent to C, then we should say that A is equivalent to C, right? We also need to offer the consistency checking support. So, for example, if I say X is an instance of both class A and class B, and at the same time you are saying that A and B are disjoint classes, so that means we have an inconsistency in our design, right? So these are the things we can consider while we are thinking about reasoning and defining the formal semantics, right? Now, why we are going for one another language? So you know that RDF schema, which is basically RDFS, was powerful enough to represent knowledge about RDF data, right? So let us see why we are going for a new language or more expressive language like OWL. So first thing, that the properties in RDFS, they are whenever we define the constraints of the properties, and what are the kind of constraints you can define on the property? You can define either domain and the range of the properties, right? Now in RDFS, this domain and range, they are not localized. So what do we mean by that? So if we say that you have one property, say eats, right? Now you say the domain of eats, it's a plant, right? Say ex, sorry, say animal, or say elephant, right? And we say the range of it should be RDFS. The range of eats is say plant, right? Now what you are saying here, the elephants, they can eat plant, but what about say lion? They also eat, right? And they do not eat plant, they eat something other than plants, say maybe meat, right? So in that case, you see that after you have defined the range of eats to be say plant, it is a kind of having a global effect. So whenever you are having the mention of the eats property, the range will always be taken to be a class plant, right? So that's why we say that in RDFS, this domain and range restriction, they are not localized. But we cannot really represent something like this. Cows eat only plant while the other animals eat meat too, right? So the eat property for cow, it is having the range to be plant, but for the other animals, the eat is having the range to be the meat, which is different than plant, right? And that is what you cannot really express in RDFS, right? And this is a very valid requirement. We know that different segment of different species, they eat different things, right? Now we cannot define the disjointness of the classes in RDFS, right? In RDFS we cannot really say that male and female are two disjoint classes, right? But again, in the real modeling scenario, you need these kind of expressions to be there, right? You cannot really think about Boolean combination of the classes. So, can we define the person class to be equivalent to the disjoint union of male and female, disjoint union of male and female class? So, this is what you cannot do in RDFS because you do not have any construct to define the union of two classes or intersection of the two classes. So you cannot really combine different classes or the concepts in using Boolean operators, right? Uh, in RDFS, you cannot impose cardinality restriction. So you can impose domain or range restriction, but you cannot restrict the number of values one property can take. So for example, if you want to represent something like this, a person has exactly two biological parents. So this is what you cannot represent with RDFS, right? And also, we know that some properties, they have special characteristics. So these are kind of traits of different properties. For example, as we have mentioned in the earlier example, that has ancestor is transitive, right? Or say parallel to each other. So that is a kind of symmetric property. A property can be unique. So the value that a property can take for one subject, that has to be defined as unique, and which is not really possible with RDFS. And in RDFS, we cannot also define inverse of another property. I cannot say that, say, is taught by or teaches. These are two inverse properties. I cannot say that the is taught by is an inverse of teaches or vice versa. So this, like, we cannot define in RDFS, right? So you can see that there are various limitations of RDFS, right? So we need one language which is more expressive than RDFS, and there comes the relevance of OWL. But this OWL has got different other precursors. So DARPA, they started on a language which is called DAML, and they are kind of trying to come up with a language which can describe an ontology. And this ontology inference layer, it is also an initiative to define a language for ontology. And both of them, they are based on RDF. So whatever we'll be doing in semantic web, that will be based on RDF. So we are not really going away from RDF. So this is a very simple platform and yet powerful platform to represent everything that we are describing in semantic web. So we also follow, so this DML and OIL, they also followed this RDF formalism, right? Now, after a few years, these specifications, EML specification and this OIL specification, which is ontology inference layer specification, they merge together to form DAML OIL, and basically this is a precursor to what we call as OWL today. And everything that you can see, every specification as you see, they are based on RDF. So we are following the same simple structure, right? So if we look at the semantic web technology stack, we are sitting here. We have talked about RDFS, SparkQL, etc., etc. So we'll be focusing at this point of time. So this is a very important component of the semantic web stack, and we'll be spending a significant amount of time on this particular concept of OWL. Now, let us have a quick look at the connection between OWL and RDFS. So, they are very closely knit. It is not like this OWL is a completely different language than RDFS. So, let us have a look at it, how they are basically related. So, they are basically related in the sense that they, both of them are following the same structure, subject, predicate and object. They are following the same data model, right? Same triple base data model, right? This OWL, they extend the RDF vocabulary. This OWL language specification extends the RDFS vocabulary. So whatever vocabulary you have in RDFS, we have an extension of it, right? And in OWL, what we are doing, we are including more complex relations or the classes or the properties to make the language more expressive. So that is exactly what we are doing, right? So if I try to give an example of such an extension, you can see this part, the upper part, the blue part is coming from RDFS. So this is coming from RDFS. And the lower part, so this is a very small fragment of our language. What you see in the lower part in green bubbles, they are from the OWL domain, right? And you can see that there is a very clear connection between OWL class and RDFS class. So this OWL class is a subclass of, or subclass of RDFS class. This object property is a subclass of RDF property. Object property is a subclass of RDF property. And data type property, which is defined in OWL, is also a subclass of RDF property, right? So we'll talk about this object property and data type property in a more detailed way in the subsequent part, right? But as of now, you just think of these to be different owl concepts, and we are just extending the RDFS concepts to design our owl concept. Now, there are three broad species of owl depending on their expressive power. So, this species can be thought of in different dimensions. So, in this classification, whatever I am going to present, this is based on the dimension of expressive power. Expressive power, right? But there are other dimensions to which we can find other kind of species of owl, right? Now, the most expressive owl family is owl full. So, you have everything here. So, you have all the owl primitives, and most important thing is it is fully compatible with RDF and RDFS. So, every RDF or RDFS document is one. If every owl document is one RDFS document or RDF document, right? The advantage of having this is that it is very expressive and it is fully compatible with RDF or RDFS specific, right? But the cons is, so as this is more expressive, you might have inferences which are undecidable. So you may end up with the domain of undecidability. And what is that domain? So that domain is, if you put forward a reasoning question, a query to the system that is following this owl full specification, you may not get any answer with a bounded amount of time, right? So the inference in that case is called undecidable, right? And if the inference is undecidable, then the reasoning is not that efficient, right? So you do not have any guarantee on the completeness or efficiency, right? This owl DL is basically following the description logic formalism, and description logic is so this set is basically this owl DL consists of a set of constructs which is a subset of the constructs which you have seen in owl full. So you can say that this owl DL is owl subclass of owl full. So you strip off some of the owl full vocabulary items in the language and you get this owl DL, right? And you cannot have full compatibility with RDF or RDFS primitive. So there are some restrictions there also. The advantage is that we have a very efficient reasoning support, and this will guarantee decidability. So this is very important. So this will guarantee decidability, right? So but the cons is it is not fully compatible with RDF, and in that case you cannot say that every RDF document is is an owl document, right? So you cannot always claim that. The most liked version is the owl light. So here we are uh, stripping off other more functionalities from the owl DL, and we are getting owl light. So in that sense you can say this owl light is a subclass of owl DL, right? So the relations that exist between this owl light DL and full, so every owl light document is one owl DL document, and every owl DL document is one owl full document, right? So coming to RDF Lite, so we have got more restricted use of these OWL vocabularies and the constructs. So, but they are very easy to write or easy to use, and they are mostly used in the teaching learning scenario. So they are not used in a real scenario in most of the cases, because the kind of knowledge that you can express with our light will be much more simpler than that you can express with RDL, sorry, owl DL or owl full, right? So needless to say, it will be having very efficient reasoning support, and it will be very easy to grasp and implement, right? And cons of course, you know that we have got restricted expressivity because we are having this efficient reasoning support. They do not go with each other, right? So with this, let us come to the elements that we have in OWL, right? So first we'll start with the constructs that are in OWL 1. So the baseline constructs, then we'll be going to the constructs that are in OWL 2, right? So the first thing that you can do in OWL is to define one OWL class, right? So it is similar to defining one RDFS class, right? So we can define one RDFS class. Likewise, we can define one OWL class, right? So here we are trying to define a class associate professor. So we'll be doing kind of similar thing as we did in RDFS. So we are defining this associate professor to be a one OWL class, and we are defining this to be a subclass of academic staff member. So here we are combining this OWL specification or this OWL construct with RDFS construct. So assuming that these two are compatible, right? So if we try to convert this or represent this the same thing in first order logic. So this is what I'll be keep on doing while I'll be describing this syntactic element of OWL. So I'll be trying to come up with the corresponding first order logic form of the construct that we are discussing, right? So why I am doing this? Because we know we are already conversant with first order logic way of writing the thing, right? So if we write this first order logic form of these statements, the statements will be made much more clearer or much more concrete, right? So what could be the possible representation, first order logic representation for this? So you're trying to define, so every class will be represented as one unary predicate in first order logic. So we define this associate professor. So associate professor. So for all the thing who are associate professor, that implies that person is one academic staff member, right? So again, it is a class. So it should be represented as one predicate, academic staff member, right? X, right? Now we have got a subclass relationship between this associate professor. So it's like this set of associate professor, the set of associate professor. So let me draw it properly. So we have a set which is the academic staff member. So this is the set of academic staff member, and this is the set of associate professor, right? So we are saying that something that is a member of associate class also a member of the academic staff member class, but not vice versa. So that means that we should represent this using a forward implication, right? Now, how do we represent this fact that someone who is an associate professor is not either a professor or an associate professor? So that means we are defining this associate professor to be disjoint with professor and as well as to be disjoint with assistant professor, right? So these three classes are mutually disjoint with each other. So this is how we can represent the fact. So we are saying we are defining this class, we are describing this class, this associate professor, and we are saying that this is disjoint, OWL disjoint with. So this is another vocabulary item which ensures which helps you to declare two classes to be disjoint with each other, right? So I'm saying that associate professor is disjoint with professor and associate professor with disjoint with assistant, right? So how we can represent this in first order logic? So basically this is how we can represent. So for all x, if this x is associate prof, so that means this person X, I'm using X. So this entity X is not a professor. right? And also the vice versa would also be true. And that's how we represent two classes to be disjoint. And we can do that similarly for the assistant relationship between the associate and the assistant, right? So here represent the disjoint relationship, right? Now, how do you say that? How do you represent this fact? Define faculty class to be equivalent to academic staff member class. So we are trying to define the faculty class to be equivalent to staff member class, and this is very easy to do. But let us try to see how do we do it with the help of OWL, right? So for that we have a construct called OWL equivalent class, right? So I'm saying that faculty is an equivalent class of academic staff member, right? So this is how we are defined, right? And you know that how to represent this in first order logic. So you say for all x, faculty x both way implies is actually equivalent to equivalent class academic staff member x, right? Now you can define your own class, so depending on the domain you are interested in or you are writing the application for, so define the classes as you want. But there are two special classes in OWL which have got special meanings. So the first class is called the OWL thing, which is basically super class of everything. So this OWL thing class is super class of every class, super class of every class, right? So you can see you have a class hierarchy. So you can have something like this, then this, so and so forth, right? So everything by the rule of transitivity is a subclass of this OWL thing class. So in that sense, whatever individuals you may be having, they are the member of this thing class. So this thing class is the class of all the individuals. So for example, if you say that a particular individual I, it belongs to this class. So by the rule of transitivity and the rule of subclass property, we can infer this I to be the instance of this class also, right? The dual of this thing class, is OWL nothing. So it is basically the complement of this OWL thing. So this OWL nothing is basically an empty set. It does not contain any individual, and you can see that this OWL nothing class is the subclass of any class. So as we consider this OWL thing to be the superclass of any class, OWL nothing is the subclass of any class. And this particular structure is called a lattice structure. So in lattice structure, you have a direction. You start with something, you keep on expanding the lattice by branching out like this, right? And finally, you converge to another class, which is basically this. So this particular structure is called a lattice structure. Now, if you think of the class subclass hierarchy of an ontology, it is basically a lattice, right? Now, in the introductory slides, I have talked about two types of properties. One is the object set of object properties, the other is the set of data type properties. So this is required because of the way RDF works, right? So in RDF, if you have a property, say you have one subject, you have a predicate, then there is a corresponding object, right? Now this object can be one resource or it can be one value, right? Whenever it is acting as a resource, whenever it is a resource, then that kind of property is called object property. Why? Because the range, whatever is appearing in the range position, is an object or entity, right? But for the value, if we select, if we see that the object position is a value, then we are talking about some data. We are representing some data, numerical data, or concrete data about a subject. So what we are trying to say is P O, where O is value. So for example, age, height, etc., etc., right? So they are representing some data about this subject, right? So that's why these properties, these kind of properties here are called data type properties, right? So these object properties, they have got other names also. We can use this name going forward. So these object properties are also called abstract roles, right? So they are trying to establish relationship between two abstract classes. So that's why they are called abstract roles also, right? So let us have an example of an object property, right? So if we try to define the relation is dot by, a property is dot by, this is dot by is should be having one course. So in the domain of this, we will be having a course, right? And in the range, we'll be having some faculty maybe. So basically, this is dot by is connecting two classes. So that's why it should be modeled as an object property, right? Now here we are trying to define this object property to be having to have the domain to be course, which is this. So here also we are mixing RDFS with OWL, right? And the range to be academic staff member. So the faculty is also an academic staff member. So the range of this property is academic staff member. And also we are saying that this particular property is dot by is a sub property of another property involves, right? So we are also saying that this is dot by property is a sub property of involves. And we know the semantics of sub property as we have studied RDFS vocabulary, right? Now we can define the inverse of properties using in OWL. So that would be done by using this particular construct, which is OWL inverse of, right? We are trying to represent the fact that teaches, which is a new property to us. So this is a new property. Assume that we have already talked about is dot by. We are defining this property to be inverse of is dot by. Now assuming that we have already defined the domain and range of is dot by, which we actually did in the earlier slide, the domain of is dot by is course and the range of is dot by is academic staff member. So we don't need to specify the domain and range of this teaches property, because we know that a domain and the range will be flipped, right? So how do you represent this in first order logic? So basically, if we have two things, the x, y, and we just say this teaches x, y imply is dot by x, y, right? And vice versa, right? The domain and range will be exchanged. So similarly, you can define two properties to be equivalent property. We are just basically saying lectures in is an equivalent property of teachers, right? This is very simple to follow. Now, as we have seen that we can put forward restrictions over the properties in RDFS, right? So we can impose domain and range restrictions, right? And we had seen that what is the difficulty, what is the kind of limitation of that kind of definition. We cannot define the properties, the scopes of the properties or the restriction of the properties locally. So that would be achieved in OWL by using some other kind of restrictions, right? So for example, you want that a property takes all the values from a particular class, right? So for example, if I want to define that the cows, they eat only plant, right? So we can take one cow, say C1. So it can eat many things. Say it's say E1. It can say eat uh, E2, and it can say eat say En, right? So whatever this cow C1 is eating or any cow is eating, this should be instances of, so these are all instances of or RDF type plant. So all values that the range can take for a property, they should belong to a particular class. So this kind of thing we are trying to define, right? We are trying to define something, we are trying to define a class for which all the values of a property belong to a particular pre-specified class, right? So for that we will be using this construct all values form, right? So let us try to define something like first year courses are taught by only professors, right? So we are trying to define the class first year courses, and what we know that they are taught by only professors, right? Now let us consider two classes. One is the class of first year courses, right? And the other class, so this class will have instances, right? Will be having instances that are taught by professors, right? So I'm not saying explicitly that these are the courses. So you can think this to be one anonymous class. We are not defining these classes. We are not naming this class, right? But we are representing this class by specifying this statement. These are the kind of entities that are taught by professors. So what kind of entities that they are? So let us take this entity to be say x1, right? X1, right? And this x1 is taught by say p1, right? And x1 is say is taught by say p2, right? You can be having another x, say x2. Again, this x2 is also taught by say p3, right? But in all the cases here, this should belong to say professor, right? This should also belong to professor. Let's take another example, say x3. Now we say it is taught by someone, say p5, who belong to say the magician, right? So this x1 would be included here, x2 would be included here, but x3 will not be included here because x3 is taught by someone who is not a professor, who is a magician, and we assume that this professor and magician, they are disjoint class, right? We also say that professor and you take intersection with magician, this is empty, right? So in that sense, x1 and x2 would be the instances that are belonging to this anonymous class, right? And we are trying to say that this fyc is a subclass of this class, right? So this is what exactly we are trying to model here, right? So let us see what would be the kind of representation. So let me wipe this out. So what we have, we are defining this first year course, right? So this first year course is a subclass of, right? Uh, so we have a subclass relationship. So this is a subclass of another class. And this another class, this particular class is represented using this piece of code, XML code. We are saying that this is a restriction class. So this is also a class. This is called a restriction class. And this restriction class takes into account two things. One is on which property we are imposing the restriction, and we know that which property you are imposing the restriction on, which is basically is dot by, right? And what are the all values that the object of this property will take? It will be the professors only, right? They will all belong to the class of professor, right? And as they all belong to this class of professor, we use all values from, right? So again, let me try to rephrase. So this particular first year course is a subclass of our restriction class, which is a kind of anonymous class, right? And this anonymous class has got two entries. One is the property on which we are putting the restriction and what kind of restriction. So which property, which prop, and the second part is what restriction. The restriction is that the all values that the property will be taking in its object position should be member of this professor, right? So that is what we are trying to mean, right? Now let us try to draw or write the equivalent first order logic statement for this specification, right? So we are defining this first year courses. So first year course, first year course. So something is a first year course. So for all course, something is called a first year course if, because we have one subclass thing, right? So if this follows something, what does it follow? So you have got is taught by. Is taught by, this course will be taught by someone, taught by. So you have a professor who will be teaching a course, and you have all the, so you need to check with all the pins, right? So all the entities that are teaching this particular course, that implies this particular entity would belong to the professor class, right? So with this part, we are basically modeling this restriction, right? And this is basically representing this first year course class, right? Now you can see that how we can draw equivalence between this specification and this specification. So you have already studied, given one natural language statement, how you can translate that into a first order logic statement. And you can see that this has got a kind of one-to-one correspondence with the OWL specification, right? So in one sense, this is a kind of universal quantification that we are talking about. We are using this for all. Now, as we can restrict the object to all become the instances of a particular class, we can also say something like it is not required that all of them they belong to a particular class. If at least one of them belong to a particular class, then that will do the job for us. So you can see that this is kind of having similarity with the existential quantifier, right, in first order laws. Right. So let us have an example and then I'll try to illustrate what we are trying to get. So we're trying to define the concept like all academic staff members must teach at least one undergraduate, right? So here you can see that we have just said that at least one. So it is not required that the academic staff member they teach only undergraduate courses. So earlier we had used this keyword only, but here we are using at least. So that is the difference. Let us try to the graphical form, right? So you have these academic staff members. So you have got academic staff member, which is a class, a set, right? Now you have got another anonymous set, teach at least one undergraduate course, right? So you'll be using or one undergraduate is taught by the first, right? So we'll be using the same thing, right? Now here we are having a same relation, having a set which is basically representing uh, mm, the elements that teach at least one undergraduate course, right? And we want this to be a subset of it, right? So let us see how do we represent this in OWL form, right? So we are using the teaches relation for this and we are defining this academic staff member. This academic staff member is a subclass of one anonymous class, and this anonymous class is a restriction class, and the first thing is on which property we are putting the restriction, which is teaches, right? So we have something, say x1, some entity which teaches say c1, right? And this x1 also teaches this c2, right? Now I'm mentioning that c1 is a type of UG course, right? We can say that C2 is also a kind of UG course, but let us try to name it as one PG course. So this is one example. Let us take another example, say X2. So I'm running out of space. We have got X2, right? And X2 teaches say C3, and C3 is a type of UG course, UGC, right? It also teaches say C4, and it is also of type say UGC. The third case is X3. It teaches say C5, which is of type say PG course, right? Now let us see what are the elements that will be included in this set. Let me remove the inside part of this set, right? So if we look at the first entity here, X1, X1 teaches C1, which is a kind of UG course, teaches C2, which is a kind of PG course. So this is ensured that at least one course which is C1, which is a kind of UG course, and this is taught by X1. So we will be including X1 here. Now coming to X2, X2 is teaching two courses C3 and C4, and both of them are kind of or type of UGC, and they will be, this X2 will also be included because it is satisfying the at least one condition, at least one condition, right? So it is not equivalent to only, right? Now coming to X3, X3 teaches C5, which is of type PGC, and assuming that PGC and UGC, they are disjoint. So this PGC and UGC, they are disjoint. Then we see that this X3 does teach something which is not UGC. So it does not contain at least one course that it teaches which is UGC. Then we will not be including this in this particular set. So you see, this is one anonymous set. The individuals that are kind of satisfying this criteria will be included in this set, right? And this academic staff member basically is a subset of this. That's how we are defining this academic staff member. So let us try to write the corresponding first order logic form, right? So we are again trying to define this academic staff. So for all, say A, acad staff member A. So this will imply that there exists at least one course, right? At least one. There exists at least one course, that is one undergraduate course, right? So UGC C. So with this, I ensure that this is a type of undergraduate course, right? And teaches A. So this is the corresponding first order logic representation of this OWL representation, right? And as we have mentioned earlier, this is modeling the existential quantifier. Now, in the property domain, you can also put restriction to be to the object to made equal to some exact value, right? So for that, we'll be using as value construct, right? So here we are trying to define the concept mathematics courses are taught by the staff member with ID test, right? So again, we are trying to see that this math course is a subclass of another anonymous class, which is a kind of restriction class. And this restriction class is putting restriction on the property is taught by, and the value should be a concrete value apart from a class instead of a class, right? So what could be the possible first order logic representation for this? So we are saying for all C, math course C implies is taught by C, then 949352. We don't need any existential quantifier or universal quantifier here, right? So there are other kind of property restrictions. This minimum and maximum cardinality restriction basically imposing restriction on the number of values a property can take, right? So if we want to set the maximum limit, we use max cardinality. If we want to set the minimum limit, we use mean cardinality, right? So let us try to represent this. Every course is taught by at least someone, right? So this someone, I'm not saying whether it would be a professor or someone else, right? So every course should be taught by at least someone. It's a very much more generic axiom that the axioms that we have discussed in the last few examples, right? So as we are saying at least, so we should model it using mean cardinality. right? So the way we will be representing this in OWL, so this course is a subclass of one anonymous restriction class, and the restriction is on is dot by, and the minimum cardinality for this particular restriction would be 1, right? So basically, if you have say x1 is say taught by say someone, say it can be anyone, person, right? So this x1 will be included in this set, this particular set. But if you have got say x2 which does not have any is dot by relation going out from here, then in that case x2 will not be included in this particular class, right? Now if we try to model this in first order logic, how will it look like, right? So we are trying to define a subclass relation, right? So we say course, a course C is a course if there exists at least one X, and this course is taught by X. That's it. So that's how we can represent this using first order logic, right? Now, how do we model the max cardinality? Basically, we will be replacing this with a max cardinality, and we can set some value. So, for example, 1, right? So, we can play with the construct. We can try to find out what would be the corresponding first order logic representation for the owl representation, right? So with this, let us stop at this point, and in the next lecture, we'll start talking about some special characteristics of the different constructs that we have or properties that we have in OWL. Thank you very much.